So, without further ado, I'd like to introduce Gijs van der Velden.
So, thanks. Thanks for the invite, and I think you're going to hear about the Rainforest Company now. We definitely tried and failed a lot, but all that failing led to this. So 5 years ago, we thought we invented at least a 3D metal printing method that wasn't around yet, and we immediately got the vision of printing something big, something constructive, something that would show people that now there was a 3D printing method around that you could really build bridges with and large structures. So this is a route that we set out for in a vision, and our vision basically all surrounds robots. So what we think is that the industrial robot that used to do the same repetitive move for 1 million times is now going to be the platform for autonomous and ever-changing jobs on the build side or wherever you need it. So what we do with these robots is teach them how to react to ever-changing environments. So when we thought about this vision of building a bridge with robots that crawl over its own support structure, we really needed a method that the robot understands where it is all the time and is able to adapt its welding program towards it. So we are from a strange breed. So we are not a metal company, we are not a welding company, not a robotics company. We started from a design agency, and this design agency developed a way of designing based on algorithms. And what we did was we gave it one mechanical engineering problem. So how, if you get the choice, you will solve the problem of a chair. So we gave a seat and a backrest, and the whole chair was then calculated by the algorithm, taking away all the materials that you don't need based on the way bones grow and bones solve the engineering problem in your body. And the good thing about this is that you get a very nice, elegant biomimicry kind of design. But the bad thing about this is that there is no simple way of producing this with the standard methods that we have available. So in 2006 was the first time as an agency we got involved with 3D printing. So 3D metal printing didn't exist yet, but fortunately we found a guy in the north of Holland that had created a sand printer. So with sand and a binder he could print these most amazing molds that we could use to pour aluminum in, and it could cool down at a very good rate so that the whole chair wouldn't fall apart, tear apart due to all the tension in there. And of course after that we still had to do like 6 weeks of manual finishing and polishing to make it presentable. But this is a route that we have taken ever since. So we take on these new technologies. We try to imagine what's the most beautiful, the most amazing thing you could make with it, and just start trying. And we start with very small steps. So we think what's the most important thing that we have to solve now. We try to solve it, see what comes out, and then decide on the next step. So I have a movie that shows well the way we like to work.
Og de tekniske tegningene, og Martin som begynner å bli ferdig med midget. Det er bra. Ja. Får du nok batterier til boligkammer? Ja, jeg har masse ekstra batterier også. Henrik! Kjapp deg ned, vi må ut! Kjapp deg, Henrik. Kom Jesus! Yes! Dritbra! Jesus, det er nydelig! Det er dritbra! Det er nydelig!
So this movie is all about, I guess, the reason why many of you started an engineering career as well. Is, I mean, the fun of just building something, trying it out, seeing if it works. That's really the kind of curiosity also that brings us together. And you probably don't need all the skills immediately already to do all these things. I mean, these guys clearly didn't have all the welding certifications that they might need for building something like this. But it's about the enthusiasm and the will and a clear vision where to go. So we continued on our search, and we really like this 3D printing because once you're able to design on your screen, you can now design the most fabulous things, but still making them, making the real life object is very, very challenging often. With this, we got to experiment with the metal 3D printing technology that was around in 2014. So what you see is that we did the same algorithmic approach. We took away material where you didn't need it and only left it where it was really essential. And you got a very lightweight aluminum chair that you could literally see through the back and some of the parts under there. So the technology we used for this is a SLM technology. So basically you put a layer of powder on top of another layer and you only solidify where you want it with a laser. And this allows you to build up very beautiful, very delicate parts in metal. And this technology is now commercially available and it's used for spacecrafts and in airplanes. So we tried it out, and what we found is that for larger structures, it's actually inconvenient technology. So the build volumes are around a shoebox, maybe 2 shoeboxes on top of each other, but it doesn't seem that it's going to grow much bigger than that. And yeah, assembly process of this actually made it quite a nuisance. So it took us a couple of weeks to assemble everything. So making a chair like this was actually a lot of hand labor. And it's also quite costly. So this technology comes in at around 4,000 or 5,000 euros per build volume. So as you can see, if you want to make bigger metal objects, it's not really the right candidate. So we started to think, how can we solve this problem? And one of the things that we saw out there was that we could get these second-hand car robots, and we can get students in. They all knew Rhino, Grasshopper, so they were able to do parametric design and coding, very simple, but at least that made this robot all of a sudden a much more flexible machine. So we got a couple of students in, and we told them we want to build a 3D printer. So we started with a resin printer, but it worked well, but we didn't really know what we could make with that plastic material that came out. So we tried the same concept with metal. So what we did was a regular MIG machine, standard off-the-shelf robot, and we created a little bit of software with that and started playing around with it. We just wanted to see what we could build with that. So here we started making lines, so we could actually draw mid-air, and we just put dot on dot, waited long enough so it was cooled down and ready for the next dot. And we created a software package around it that allowed us to do all these drawings. And what we also did was put every experiment online. So initially we were like, oh, we should patent this and we should see if we can keep it closed until we have clear what the real value of this is. But then we decided, no, I mean, we should just open up and show everybody what we're doing, and hopefully this will bring us back more than what we give up by not patenting it, by not keeping it close to the chest. And this worked. So we got people that asked us if we could print stuff for them, like the BBA architects in Miami. So this is in a Herzog de Meuron museum on the beach side, and this is an outdoor bar. And they actually wanted to make this already before they seen our technology, but they couldn't get a metal worker to do it for a reasonable amount of money. And we were actually being able to do this in a competitive pricing. It was a big learning. So as you can imagine, you know, when we printed a couple of these lines, that was still quite okay. You know, we had one guy looking at the print all the time, but then all of a sudden we had to make 2,000 meters of line, that was a bigger challenge. But it learned us how to create a technology that was actually able to also come to a sort of a production level. So we tried out many different materials, many different shapes. Most of these we could do for artists. The good thing about the artists was that they have a different idea of what's already good enough for them. So when you can do something that is not possible with other technologies, they will be interested in starting to experiment with it. And this really paved the way for us. So we literally did all these jobs and paid our software engineers to create the next step. So eventually we formed all of our knowledge over the 3, 4, 5 years that we worked on it into a software package that we needed. So we were not intending to make a software package at the beginning, but we noticed that there was no tool around there. And yeah, instead of being very hands-on for every print we had to do, we said, okay, we have to automate this because eventually, if we prove to the world that this technology is really worth investing in, they will want this tool. So what we created is a very simple COM solution where you calibrate the material. Based on that calibration information, we check whether the print is feasible. We slice it, we create a toolpath, and we have quite a few sensors that check on the process to see whether everything is going right. And if you have the knowledge about a certain weld pattern and what is right, then you can also intervene automatically. So this is really the basis for us to come to yeah, more industrial manufacturing. So we now have 8 robots in our facility, and usually they are guarded by 1 or 2 people, and they can produce on average, so 2-3 kilos per hour per robot. So yeah, for steel industry, I heard a lot of talk about 2 tons per hour of work yesterday. I mean, in our case, we're talking about volumes that are a lot smaller, but you can make unique items that are not possible to create with the standard metal works today. So every time we create something new, like in this case, the software, and we want to promote it, we put it into a shape that people recognize and appeals to people. So in this case, we decided to create a bicycle, so to show people where the state of MX3D was and how we're doing with the software. So we now left this unique building and went to a more proper industrial area, but this place was really nice to get started. Only the neighbors were not so happy with us grinding all the time. So we do a lot of optimization. So we work together with Altair, for instance, because every kilo you can take off of your printed part saves you an hour of time. So that's a really big win. So that's also why the 3D printed objects are usually optimized and lightweight. It's not necessarily because the end client wants that, but it's just a lot cheaper to design that way. So 3D printing and this technology in general, they have this driving force to change the way you design. And it's also one of the main things that we come across. So people always ask us to give a quote for something they already have spec'd out for a traditional way of manufacturing. And then often we say is like either we start all new and we create the design together based on the design parameters that we have, or we're not going to do it because we're never going to be competitive with the old way of making. MX3D is now 15 people. We have quite a few European funding projects, and one of them is the Integrate project. And there we take on so process part 3, 4, and 6 sometimes. And the other partners, they all bring other things to the table, because what we realized that we are never going to do this by ourselves. So we created our software to be very flexible, so we can take in data from other companies and also give data to companies that do the analysis for us. So this way we hope to have a sort of a second shell of companies that eventually will lift on our software as well. And this really helps us to grow much faster than we could when we had to do everything ourselves. It also allows us to not have certain skills in-house. So we are not welding experts. We definitely don't have a lot of knowledge about stresses in the material, but we have partners for that. And for them, it's also interesting to hook on to our software, because we have this sort of open architecture there. So that allows them to partner up with us, and then spread their knowledge that way. So the original vision of the 3D printed bridge was to have 2 robots, and then slowly work towards the middle while printing, as they stand on the part that they just printed. So this was a really challenging project and vision. I guess in the beginning we still really believed that it was possible, but we had no clue how long this would take. So what we did was try out every single part of this vision and to see whether it was possible. So the good thing is that we managed to actually have the robot on top of the bridge, print parts, move it, and relocate it and have it print again. But unfortunately, that was a pretty slow process. So if you do horizontal welding, the gravity takes hold of the material. So we could only print half a kilo per hour instead of 1.5 or 2, and that was what we needed because the ultimate weight of the bridge was 6 tons. So 6 tons times 3 or 2 is 12,000 hours. So that was a little bit much. So we had to take quite a few steps away from the original vision. So what we said at some point is like, okay, what is the most important part of to achieve right now? And that was to put a 3D metal printed bridge in the middle of the red light district in Amsterdam to prove to people this technology is there and it's not going away anymore. And many people thought that vision was really attractive. So a lot of partners contacted us and they asked if they could join. And what we decided early on, just as with the software, we said, okay, we're not going to make heavy paperwork contracts. We're just going to ask you what can you contribute to the project. And if you want to take away learnings from it, that's all up to you. And this gave us really self-motivated partners that had an interest in making this succeed, not just for the PR value, but also because they could learn from the project what they wanted and they could contribute what they could. And this really allowed for a very flexible way of working together with these big companies that are normally used to lock everything down in huge contracts that were too much time for us to digest. So this is the bridge that we're replacing. As you can see on the design side, it's not a big challenge. But definitely on the structural side, we have a challenge. It's one of the busiest areas in Amsterdam. We have 15 million visitors a year, and most of them, they visit the red light district. So we really had to take into account that the bridge at several points a week would be completely full, and maybe even with jumping football fans. So it will get all the maximum design load that we give it. We took the same approach. As I said, 3D printing and optimization are a marriage, a forced marriage in a way, because all the material you can save is going to save you on printing time. So we together with Autodesk, we created some algorithms that allowed us to really reduce the weight of the original design. This ultimately led into this design. So we had, I think, 1.5 years we needed to come up with this, because we, of course, also had to do a lot of buckling tests, tensile tests, the printing tests to see what geometries we could do. And this allowed us to come up with this design that we were like, okay, we can print this, we can even do it with the robots on top and printing horizontally if we want to. But then a disaster struck, because both the engineers that were working on the project and the city didn't like this. I mean, there was some safety issues. So a boat could sail into one of these big members, and if that would break, it could be a catastrophic failure. That's, of course, not a good advertisement for MX3D. And the other reason was that we couldn't put any forces on the ancient canal walls there. So we had no choice but to come up with a completely different design. And because we were already 1.5 years in and we had around 3 years of funding for this project, we said, okay, we have to do it fast. We got Arab on board, and within the course of around 2-3 months, we came up with a new concept. So we started with a U shape. We twisted it slightly because the bridge heads weren't completely parallel across each other, and these force lines that came out of that twisting, they became an essential part of the way the bridge looks, but also the way the bridge behaves. So we got Imperial College on board, and they did a very extensive analysis in Abacus. where they tried to de-risk the whole project, because we knew one thing. I mean, if we were going to print a 6,000 kilo bridge, it has to be right in one go. So of course we over-dimensioned a lot, but also we still needed the verification on the digital side. So based on all the material properties that we got from the tests, we got these results. And when we saw this, we decided we just have to go for it and start printing. So we first printed a 2-meter part. This took us probably a little bit less than a month. And with that part, we said, okay, now we have our first proof of concept. Let's test it. So we got sensors on there, and we did all the tests that we could imagine to prove that the predictions that came from the Abacus model were still valid on this print. Because of course the initial model was based on the STL file. It's super smooth and there's no imperfections there. So we needed to know what the effect of all these changes were. But it turned out that the model and the actual behavior were fairly close together. Yeah, the engineers were approving us to continuing and to create the full bridge. So these sensors, they got on there initially for testing. And then we thought it would also be very nice if we have these sensors in place while the bridge is in its location. So we have sort of a bridge health monitoring system, because nobody really knew how a complex, monolithic block of stainless steel would behave under sunshine. I mean, we've already seen that it becomes super warm. So is it going to twist? How is it going to behave? So we wanted to know everything on that side. So if we were making a new bridge, we could use that information. So we put all that information in a digital twin. We have a mathematical institute in London that works on that, the Alan Turing Institute. And they create this digital twin based on all the information that we gather. So all the data from the bridge health monitoring system, but also from the material testing. It can be put in. We can do all kinds of virtual tests on new designs. So we can do a lot more testing already in the virtual world before we could consider printing it. And the good thing is also that we can update. So in the beginning, of course, our printing was less controlled than it is now. So we can continuously update this model with new values that we find. So we with Dasher 360, it's an Autodesk interface that allows you really to get a good visual of all the IoT aspects of your project. So what we think is going to happen with these digital twins is that allows you as an architect, as a designer, to come up with new ways of designing. So instead of designing every bridge from scratch, based on your knowledge, you're going to make rules of design and implement that in an algorithm and let that algorithm give you all the options that are out there. And you, as an engineer and as an architect, you pick out the one that is the most suitable for the specific purpose that you have. So in this case, the architecture or designer's role was still quite big, because we really wanted to make a good note with the historic place where it is. But I guess in the future, when it's more about efficiency and about cost reduction, it's really going to be more and more the algorithms that determine what the best solution are. So for some of you who haven't seen this, this is a nice summary movie of the bridge. I think it shows quite well all the stages we went through. So I've said this before with different dates, but the date of placement now looks like to be June. We thought about placing it in March, but the electricity company that has to replace the electricity box that's in the way takes a little bit more time than we expected. So we get into all these practical parts of getting a permit, getting the electricity company to move things around, and that made that from a 3-year project, it eventually became a 5-year project. But for us, it's not necessarily a bad thing. The sensor project really got 2 years more to evolve. So one of the ideas now is to really teach the bridge health monitoring system what's going on by putting cameras on top of the bridge, making stickmen of everybody, and really identifying in a very high level of detail what people are doing. So not just counting heads, but are they stopping? Are they making a selfie? Are they selling drugs on the bridge? Whatever kind of information can be useful for the city to know, will get out of these data from the bridge. So first, we need the cameras. Once the cameras have taught the bridge health monitoring system what they are experiencing, we can take away the cameras and just based on that bridge health monitoring system, we have all of a sudden have a world more of data to work with. At the same time, as MX3D, we are looking further in the future. And unfortunately, what we see now is not bigger, so we don't think about printing bridges of 50 meters yet. Where we see the sort of the magic spot is somewhere between 50 kilos and 1,000 kilos. As I said, I mean, you need something like two hours or 2 kilos per hour. So if you want to make something of 1,000 kilos, it takes you 500 hours, which 24/7 production you can do in 3-4 weeks. But that's still relatively long for most metal productions, of course. So we target now smaller items that are unique, or at least in a small batch. And usually are a good target also to trim down with the algorithmic design. So connector in steel connections, that's one of the items that larger architecture firms always come to us for. So this is a project that we did with Takanaka, is a Japanese building company, and they really want to understand how they can do parametric design and then have the most complicated parts that now take away a lot of time from skilled welders, how to make that fully automated. So this is one of these concepts. So we just put in 4 beams, and then we had the algorithmic software determine what it should look like. And in this case, we could even open it up on the inside, because if you have these bigger nodes, they often put concrete inside. I think it's for fire resistance and bending, extra bending force. But I guess most of you will know this better than me. And this was the end product. As you can see, it's still relatively rough on the outside, which can cause some engineering concerns about fatigue strength in this. But it is part of this technology. So we use a MIG welding technology, and it's simply not going to be much smoother than 0.5 millimeters. So either you have to finish it, or we have to take it into the calculations and make sure that it's not a cause of alarm. So this is the vision that we're working towards with the Takanaka. So we have set up a research project where we defined what we need to know and what we need to prove to the certification commission before we can actually build a structure like this. And that's what we're going to do next year. And then hopefully we can pick out a nice building where we can apply it just after we've proven that it's all fine. We also had a New Zealand partner coming up to us and asking whether we could work together. And so it's TIDA, might be familiar with you guys. And one of the ideas we had for the conference, because I couldn't take over too many samples, is that they would print a part so that you can see and feel by yourself what it feels like. So this is what they printed. As you can see, there's a slight umbrella in there. That's because of all the residual stresses from the welding. That's definitely something that we have to take into account all the time we design and print. But it gives a really good idea of what you can do and the level of detail you can achieve. Another project we did, and I think that's where we see a lot of advantage as well, is in the heavy equipment industry. So when you need a spare part, it probably takes you a long time before you have designed and made it ready for casting. You order it, maybe overseas, and then you get it back 4 or 5 months later. Hopefully it's all according to the norms that you put, but it's also likely that the first time is not immediately right yet. So if you have this digital manufacturing method, you can not only bring down the weight, the material that you need for a certain item, you have full digital control over your production. So once you know what is a proper way of producing a part like this, you have full control, and it takes you a factory floor of maybe 2.5 by 2.5 meters, and all of a sudden you have this like miniature casting company in your own facility. As we think it will always be hybrid manufacturing. So either you start already from an existing block, so you skip maybe the 5 tons you would have to print otherwise, and you use a standard block for that, and you start from there. Or you print and then you mill it afterwards to make sure that at the right spots you have the definition that you desire. And that's my presentation. Thank you. Just have a short video on the robot arm.